Hello everyone, I'm Yilin Wang from Zhejiang University. I'm honored to present our research, Spatial-Temporal Forgery Trace-Based Forgery Image Identification at ICCV 2025. Introduction to Forgery Image Identification Knowledge. The field of image generation was initially dominated by techniques based on generative adversarial networks and autoregressive models. The continuous evolution of these techniques led to the emergence of landmark products, such as BigGAN and DOL. However, these methods still face limitations in terms of controllability, stability, and complexity of content generation. Consequently, a new approach to image generation, the diffusion model, has gradually emerged, inspired by non-equilibrium thermodynamics. The denoising diffusion probabilistic model emerged and demonstrated excellent generative performance. Subsequently, researchers focused on optimizing its structure and improving its sampling efficiency. Against this backdrop, the latent space diffusion model emerged. Applying the diffusion process to the latent space not only improves model efficiency, but also enhances the ability to generate text-conditioned images through a cross-attention mechanism. LDM has become a significant advancement in image generation and has spawned well-known generative models such as Stable Diffusion. With the rapid development of AI-generated content technologies, such as diffusion models, AIGC has been widely applied in fields such as image generation. This has led to the proliferation of false information and the frequent occurrence of harmful activities such as malicious tampering. Furthermore, by forging images, malicious attackers can impersonate others and commit fraud, causing economic losses and a loss of social trust. Forged image recognition uses AI technology to detect forged images and prevent malicious attacks. Comparison with existing methods. Current deepfake image detection methods primarily rely on extracting handcrafted features, deep features, and frequency domain features for forgery identification. Handcrafted feature-based methods typically extract statistical features, such as color histograms, local binary patterns, and histograms of oriented gradients, to detect forged images. While these methods may be effective for early deepfakes, they are less adaptable to images generated by diffusion models and struggle to cope with evolving attack strategies. Deep feature-based methods typically utilize deep neural networks, such as CNNs, ResNets, and efficient nets to extract high-level image features for classification and discrimination. While these methods can improve detection performance to a certain extent, they often learn semantic features of the image itself rather than specifically focusing on forgery signatures, which limits the generalization ability of the forgery detection models. Frequency domain-based methods use frequency domain analysis techniques, such as Fourier transforms and wavelet transforms, to extract features from high frequencies or specific frequency bands to detect forgery signatures. However, since different AIGC generation methods may employ different generation strategies, the stability of frequency domain features is insufficient, limiting the generalization ability of these methods. This paper adopts the perspective of modeling the distribution of forged images and utilizes a generative diffusion model to extract temporal distribution features of images. We then mine forgery trace features from this semantically uncorrupted temporal distribution feature space, aiming to achieve high precision and generalization in image forgery detection. By mapping the latent temporal distribution of images, we elucidate the evolution of these temporal distribution features and identify them as indicators of temporal forgery. Furthermore, generated images are often more susceptible to forgery in high-frequency regions. We use this high-frequency information as a weight to help the model more quickly identify spatio-temporal forgery traces. The framework of spatial-temporal forgery trace-based forgery image identification. Considering that the latent space diffusion model maps data into a low-dimensional latent space through the encoder, where the distribution is more compact and easier to model, compared to the complex structure of the high-dimensional pixel space, which is difficult to model directly, we focus on extracting latent representations and analyzing them at each step of the diffusion process. To facilitate modeling distribution changes from a time domain perspective, we reshape the latent representation of each diffusion step into a one-dimensional vector. The sequential vectors from steps 1 to t are vertically concatenated to form a token set. This data format serves as the input for time domain modeling and frequency domain analysis. Based on the assumption that the latent spatial distribution of forged images tends to be smooth and has little temporal variation, we draw on the idea of unsupervised temporal anomaly representation learning and employ a trainable Gaussian kernel to compute the prior correlation between time steps. We introduce an adjustable scale parameter sigma to adapt to different temporal series patterns. The unimodal nature of the Gaussian kernel enhances the correlation between local time steps, making the non-stationary characteristics of real images more prominent and the smoothly evolving patterns of forged images easier to distinguish. This improves the temporal modeling capabilities for forgery detection. Forged images often exhibit unusual spatial similarities, e.g., excessive symmetry, or inconsistencies, e.g., color or texture mismatches. To address this issue, we extract features from each dimension of the latent space and apply a self-attention mechanism to calculate spatial correlations within the latent space. This approach amplifies regions of unusual similarity or inconsistency in forged images, thereby enhancing the ability to detect forgeries. In frequency domain analysis, high-frequency details in forged images are often eliminated during gradient optimization, resulting in significant differences in their frequency characteristics from real images. To address this issue, we use the fast Fourier transform, FFT, to extract the frequency domain information of latent space features and compute frequency domain correlations to capture cross-scale feature interactions. Because forged images lose high-frequency information, the frequency domain distributions of real and forged images after the conjugate product operation exhibit distinct patterns. An inverse Fourier transform is then used to map the correlations back to the spatio-temporal domain, allowing the model to focus on the anomalous features caused by the missing frequency domain information. Experiments. To verify the model's generalization ability across diverse generative models, this section follows the GenImage evaluation criteria and compares our approach with 12 leading forgery detection models. All models are trained on the SDV 1.4 subset of GenImage and evaluated on multiple test sets. As shown, our proposed STFT achieves over 89% accuracy on the big GAN dataset and achieves state-of-the-art accuracy on 7 of the 8 subdatasets, significantly outperforming existing forgery detection methods. Following the deepface gen evaluation criteria, we compared STFT with leading generated image detection methods. Training and testing were performed on the same dataset, which contains real images, as well as images generated by 12 different forgery methods, including DAL-E. The dataset was split into training, validation, and test sets in a 7:1:2 ratio. As shown in the figure, STFT outperformed all methods in all 12 subsets. We trained the STFT on a single subset of the GenImage dataset and tested it on all 8 subsets. As shown in the table, we compared the STFT with the top 4 models in the baseline evaluation. The STFT outperformed the existing state-of-the-art method, DRCT, on GenImage and achieved the best generalization performance across all 8 subsets. Forgery detection methods based on reconstruction error often fail when the test data differs from the pre-training domain of the reconstruction model. For example, applying a model trained on animal images to plant images may misclassify real images as fakes due to excessive reconstruction error. To evaluate the robustness of STFT in this context, we used pre-trained models for the LSUN bedroom, cat, and horse categories and compared STFT with DIA and DRCT. The results in the table show that while the performance of reconstruction-based methods degrades significantly, STFT consistently maintains an AUC score above 90%, highlighting its strong generalization ability. Thank you for watching.